Okay, so let's get started. Right, so welcome to the fourth lecture of Trustworthy Machine Learning. So we had a short survey of who wants offline tutorial after the lecture, and there was no response on Discord, so I guess we don't have it. But Alex is here today, tutor, right? And he's responsible for exercise 1, so you can ask him because he's now here, or you can also use Discord or the email for asking questions. We prefer, if possible, that the questions are asked on Discord, because then we all share the same answer, kind of FAQ, right? But yeah, you can also use your this email address if you want. Okay. Otherwise, we can jump into the next topic. Well, the same topic, but the next material. So last time we were talking about different scenarios where this generalization becomes possible again, right? Because otherwise, if you don't have any information about what your target distribution is, then the problem is not solvable conceptually. And so we talked about introducing a little bit of unbiased samples and making sure the bias labels are available. So the rightmost case. In that case, we can kind of try to put more weights on those unbiased samples, right, by using the bias labels. Or in the slightly weaker case where you don't have the explicit bias labels, we can use our prior knowledge about what the bias will be in this data set. And using that prior knowledge, we kind of detect them using some mechanism. And then we can use the mechanism again to put weights on these bias samples. Ideally, we want to push down the bias samples and then put even more weights for a very small number of unbiased ones. Okay, and after doing this, your model is unbiased. So that was one axis of like how many unbiased samples are there in your training set, or bias labels are available in your training set. The other axis is what we're going to take a look at today, which is the availability of the test samples or the deployment samples, deployment scenario samples. Because once we have access to those samples, then we know the target distribution. Yes, Alex. Ah, right. Is that all right? Okay. So that's when you have a few label test samples, right? Yes.
I noticed that you didn't have a reminder about video recording. So I think you might want to check.
So this is recording now. Nice. But thanks for the reminder. I probably need that next time. Yeah. Right. So if you have access to some test samples, right? But there are two different versions of it. When you have labeled test samples and when you have unlabeled test samples. Okay, so if you have labeled test samples, it's easier than having unlabeled test samples. I'm going to talk only about this easier case, and this harder case of having unlabeled test samples, I'm not going to talk about it yet, because I'm not entirely sure if that's still possible case to solve, right? There is a paper that corresponds to this setting, but I don't fully trust if that's working in general deployment scenario. I'm going to mention which paper this is, but yeah, but I decided not to talk about this paper in a course because I don't have full trust yet. Okay. It's called test time training paper. I can probably post that on Discord. Yes. Yes, yeah. 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 So I can post a link. Okay. So let's talk about scenarios 3 now when you have a few unlabeled samples at test time. Okay. So you only have now bias training samples to start with. What can you do with these 3 cases, right? What we can actually do is to train multiple models with diverse OOD behaviors, right? So what I'm going to do is to draw different decision boundaries on these kind of samples. So you can think of this 2D plane here as kind of input space, and you're drawing some decision boundary on it such that your 3 samples are well separated. Okay, that's what classification is doing, right? So your model 1 is drawing decision boundaries like this. And actually, if you just follow the decision for model 1, then you're actually classifying all the samples according to shape, as a matter of fact. Because the first class corresponds to kind of round shape, and the second class to triangles, and so on, right? But there's nothing that forces the model to behave just like that, because your second model can just be looking at this kind of slanted decision boundary, which is not clearly cutting any of the human interpretable Q here, but just making some random kind of dissection or random partitioning of the space. And let's say your third model is doing something like this, right? But then this is good because we have all the ingredients necessary to detect or to recognize samples according to any Q that you like, right? So once we have these kind of 3 models, then all we have to do at test time is to choose the right model among those 3 samples and feed your model to your test distribution. Yes.
So in the last lecture, we saw how models are biased towards easy Qs. Wouldn't it always happen that all models would just fit to the color Q? And
yeah, that's a very great comment. So we have to do something about that, right? So we'll talk about that in the later slides. But I guess there are some slides to explain before going there. So this is a reminder slide saying we need some extra information to make cross-bias generalization possible. So yeah, I am repeating this a lot of times, but in this case, you're kind of having access to a target distribution now, right? So there are different instances where you get access to target distribution. One case is kind of domain adaptation, where you have unlabeled samples from your target domain, or test time training as well, where your deployment stage is kind of going hands in hands with your development stage. So you're kind of developing your model all the way through, meaning that you actually have access to your target domain samples. So now, where does this scenario 3 kind of fall onto? I would say it falls onto this kind of test time training stage, because now you have these 3 models ready, and you need to kind of make a choice for your model at test time. Okay, and how are you going to make a choice in your model? What I'm going to do, for example, is to label a few test samples at test time, like these ones here. So clearly what I'm looking for is the shape Q here, right? Because I'm labeling circle as one, triangle as two, and so on. So once we have this kind of labeling for a few samples from test time, then based on that, we can choose model one, because that's kind of giving me the best accuracy at test time. So what do we need for doing that? We need a few test samples labeled. And therefore, we're going to need access to a few unlabeled samples and then annotate them. And so this is an instance of this test time training where you're actually annotating a few samples at test time. So this is kind of clashing with what I said about test time training, because I said test time training corresponds to having unlabeled samples at test time. But actually, there are different versions of it, and I would still call this test time training, but with labeled samples. You're using annotation. Yes.
I have a kind of basic question, but could you maybe explain the difference between this and having unbiased training samples?
Yeah, that's
very similar.
Mhm.
Having labeled samples from the second domain or having unbiased.
Right. Yeah, that's a great comment. I noticed that too, and I agree with you that it's the same. But in practice, I think we are making a lot of simplification here. But in practice, it's very unlikely that you're going to have unbiased samples at test time. Most likely, your deployment scenario will contain a lot of biased samples, but biases that are kind of different from your training set. Okay, so in a sense, in this case, you're kind of aiming to aiming to fine-tune or adapt yourself to the specific bias at test time rather than so yeah. So yeah. So if there's yeah, I'm not sure if that was clear.
They are biased, but kind of differently.
Yeah. Exactly. Yeah. Okay. So in that case, I think there's a distinction between the two. Mm-hmm. Apart from that, you're also going to see other types of distributional shift between training and testing. And it's like this scenario is kind of making sure that you can adapt to any kind of shift at test time, because you have direct access to your test time data stream. Yes.
I have a follow-up question, also related. So we only have a few samples from the test data, and we shoot it according to that data. But how can we know that the data that we are seeing is a good representative of the whole test domain?
Yeah, so even there we have two versions. So we can adapt to your model very frequently for like every batch of data, or you can kind of trust that your distribution is not going to change for the next month, let's say, and then you just update it every month. Yeah, I'd say there are different versions of it. Yeah. Okay, so now I'm coming back to how to train such a diverse ensemble of models. So what's the recipe? Well, actually before that, even more high level. So we first have to train an ensemble of models with some diversity regularization, meaning that we should not just train some random n number of models, but we have to train models that are kind of different from each other to make sure that you're covering as large space of possible Qs as possible. And then at test time, you use a few label samples, or you can also use a bit of human inspection if that costs less annotation time. And then we can select the appropriate model that generalizes well in that case. Okay. So now the question is, how do you train this diverse ensemble? We need to train this diverse ensemble because as there was a question, right? If you just train a model n times, then all of these will be focusing on easy cues, right? And so if the first model has learned an easy cue, then probably we want the next model to learn something that is less easy or some other possibilities, right? Yeah, so how do we train such a diverse ensemble then, right? The question is, how do we encode difference between two different models, right? Because if there's a way to measure it in a differential way, then using deep learning, we can optimize for it, right? So yeah, as in other branches of deep learning, we first need to come up with a differentiable measure of what we want to measure. And here, what we are measuring is the orthogonality of input gradients. In this paper, predicting is not understanding, recognizing, and addressing underspecification in machine learning. That was presented like 2-3 weeks ago at SCCV. They present a way of making models output or focus on different types of cues by using the orthogonality of input gradients. And they measure this cosine similarity among the input gradients for the same inputs, okay? So for every input, they measure this input gradient for that input, and then make sure that the models in your ensemble are having different or orthogonal input gradients. So intuitively, what this is trying to do is, for example, let's say your features are in different regions in your image, right? Let's say there's background and there's foreground, right? And if one model is looking at the foreground, then probably there's a lot of focus in your input gradient on the foreground pattern. And then what you want to do is you wish to train the second network, which is focusing more on the background pixels. That's what they are trying to do here. And in practice, they say it makes the set of models even more diverse. Yes.
Sorry, no, I just to clarify. So the gradient got to the input pixels pertaining to the right label. Like the gradient of input pixel with regard to the right label.
Yes, I think so, but can you confirm this, Alex?
How the gradients from what's to the
But like the gradients of the actual pixel, like where you normally wouldn't propagate gradient to.
of the
Not of the weight of the network, but of the pixels.
piece of image.
Yeah.
Yeah, gradient.
Sorry.
So the ground truth labels are used for generating the input gradients. Yeah, that's an important detail. Yes. Yeah. And they look at, so this is a pairwise measure, right? So if there are n different models in your batch, in your ensemble, then you have to compute this order of n squared time, right? Because you have to measure all pairwise independence. So this is one measure, but I can think of multiple different ways of measuring difference here. For example, we can use this Hilbert-Schmidt independence criterion that we talked about last time. Although we don't have any experimental results saying, even in this case, that measure is kind of producing a diverse set of models. But what I'm saying is you can use whatever difference measure you wish to use for measuring the diversity of models for a set of models here. Okay, so this is what they're doing, right? And this is a differentiable measure, so you can use that for loss function. And here the assumption is, so this is kind of rationale why they can use the input gradient orthogonality for measuring kind of they're focused on different cues. So they define independence as the statistical independence of model outputs for a local Gaussian perturbation around every X in the input space. So what they're doing is they're perturbing their input around the small ball around its pixel space. And then they're measuring the change in the outputs for model 1 and 2. And they wish to make sure that those variations in the outputs based on these local Gaussian changes are kind of orthogonal. And if you encode this requirement in terms of a loss function, then what they get at the end of the day is this orthogonality of input gradients. Okay. Yes.
Small question, but actually, if you put some perturbation, is a bit against the idea of robustness, right? Because but I'm not quite sure, but I think the labels are staying same, but the gradients are changing, right? Because if the output changes, it's a bit against the robustness.
Okay, so yeah, we are kind of mixing terminologies here, I guess, because here we are not talking about adversarial robustness, right? First of all, and this is about explaining why you are taking input gradients to measure kind of independence.
Yeah, but like this F represents the gradients or the outputs?
The outputs, yes, the outputs. And what you want here is that model 1 and model 2 are kind of reacting in a different way to the changes in the input space, right? So in a sense, that has I have a hard time finding connection with between that and adversarial robustness.
Yeah, but like we are talking about small perturbations, right?
Yeah, exactly, yeah. Because we are talking about gradients, right? So the way this kind of result translates to gradients is by saying sigma here is very small. And those changes, according to sigma, is perfectly represented by the gradient. Because gradient is looking at the local changes, right? And based on this sigma here, the output changes will be also infinitesimal. And therefore, those changes can be encoded according to input gradients. All right, that's what they are saying. And the orthogonality of the changes or the independence of the changes are kind of encoded in terms of the orthogonality of input gradients. So making connections to adversarial robustness here, I can probably say a model is not very robust if those small changes around the X are introducing a lot of changes in the outputs. But actually, if you're just sampling from this Gaussian distribution, it's very unlikely that you're going to see such a big change, unless you sample like millions of times.
Okay, I think I'm confused of the orthogonality of the outputs because so it does not mean.
Yeah, sorry. Okay. So here, it should be actually a statistical independence rather than orthogonality. So the statistical independence between the outputs of F and 1 and 2 is translated to the orthogonality of geometrical orthogonality of input gradients. Yeah. Thank you. That clears the argument here. Yeah. Okay. And then there's one other very important concept, which is on-manifold constraint. So we're talking about two-dimensional spaces for this input space. But actually, if you increase the dimensionality of your input space, there are actually like exponentially many different ways you can draw these boundaries. And even if you have this diversity orthogonality constraint, you may find like nearly infinite number of different ways to draw decision boundaries in the input space because of the sheer dimensionality. Okay, so what you do is you use the concept of data manifold, saying actually the input space is like close to million dimensional, but the actual relevant subset inside that space is very low dimensional. And so the figure here is showing, for example, there's very low dimensional manifolds on which you're going to find these sci-fi images. But if you sample randomly from this space, then you're going to see these random pixels. So what we can do is to confine our exploration of different decision boundaries within the manifold rather than exploring all the other spaces. Okay. So what they do is they do projection first to this manifold, and then using those projected input gradients measure the orthogonality. Okay, then that constrains the freedom of the model to kind of find new directions where things are orthogonal, right? It drastically reduces the search space for the new model. And it really makes sure that you're looking at a meaningful new cube in the next model to be introduced in the ensemble. And the way they project their input gradient to the tangent space of your manifold is by using a variational autoencoder. Because what variational autoencoder does is it learns the data distribution, right? And yeah, and therefore you have the information about what's a likely data and what is not a likely data. And therefore you can project your gradient to this to the relevant space in your data space. And then you take the L2 distance between this projected gradient and the original gradient. So you're kind of forcing your input gradient to be kind of aligned with the data manifold. Okay. And now your training looks like this. So you have your training data set and models theta 1 up to theta large M. And first of all, you have your original task for predicting your model, right? I think sigma here is sigmoid or softmax. And then what you have is this independence loss, which promotes independence or orthogonality of input gradients. And you do that for m squared different pairs here. And then for every gradient, you put additional regularization, making sure that they are lying on the tangent space of the manifold. That's it. And you train it. And hopefully that generates a diverse set of models. And this is the result. And they build this kind of funny data set where you are actually collaging different data sets. So MNIST, Fashion MNIST, CIFAR, SVHN, they all have 10 classes. And then they put samples from each data set in this kind of window kind of fashion. So you put label 0 for this combination of samples, label 1 for this combination of samples, and so on. And then the model can kind of decide which one of the quadrants they should be looking at to make decision. Looking at any of the quadrants is solving the problem. But the question is which one they are choosing, right? And ideally, by training multiple networks, they should be able to get at least 4 different models that are looking at each of the quadrants. Okay. And this is the results they show. So the number they show here is the best model on each of the data set. So for example, they're gonna train, let's say, 8 models here, right? And among these 8 models, they search for the best model for MNIST, for example, or SVHN, Fashion, CIFAR 10. So if there are 4 models that are specializing in each of the component data set, then you're going to get 100% for each column here. And the average should be 100% here. And they are eventually getting something close to that, right? Meaning that you can actually train diverse set of models. And here the upper bound is given by just training your model on the target data set, which is 99.9%, 92.4%, which is very close to this 92.3%, right? Meaning that you're actually getting as good as possible on this data set. Fashion as well, you're actually very close to the upper bound, or even just there. Cypher 10 as well. So this all means that your model is actually specializing in each of the data sets that are that's in this benchmark. Right. What else to comment on? So if you just train ERM baseline, which just means you're just training the model, training one model for these kind of images, then what you're going to get is 99.8% accuracy for MNIST and random chance for all the other benchmarks. So it looks like MNIST is the easiest Q to look at in this case, right? And they also trained with like 1,000 or 128 different models. And yeah, you can go like crazy, like 1,000 different models using this method. Yeah. Okay, so summarizing what we have seen so far is we're still using samples for X and Y for training, but then we are training a lot of different hypotheses. And then we are making selection at test time based on the, oh yeah, that I didn't mention, right? So inherently by choosing the best model on each of the data set, what we are doing here is using the test time information, right? Because then we are kind of using the fact that we know we're looking for MNIST labeling, right? Or SVHA labeling. So this number here corresponds to the scenario where you have a few label samples from test time domain, okay? So that's the important bit. And that's also kind of how you can justify their way of measuring performance here. So yeah, so they are making use of test time labels in this case. All right, so that's the summary of the first part, which is feature selection problem. And on the specification, we looked into like the question is which features is going to let me generalize to new distribution. And we talked about different techniques for identifying misspecification. We looked into different ways to make this selection of cues possible. And if there's unbiased sample during training, and if those samples are kind of labeled, then you can just detect them right away. Then you can put different weights on these samples or use group DRO or domain adversarial neural network. If they are not obviously labeled, but if there's a way to kind of use your prior knowledge of those samples to detect them, then you can also use this detection method and then put different weights on them. If there's any unbiased samples, you think, then you can also rely on multiple hypotheses for these samples and then try to choose the right model at test time. So that was it for this section of the course. And we'll move to the adversarial, but we can take a 5-minute break before going there. But there's one question.
Yeah, a quick question for like the last model, which claims like 4 different stitched together images. Will you describe it as cross bias? Because isn't the test and training data the same?
I would still say this is cross bias, because what they do at test time is they break the correlation among all these 4 quadrants. For example, this car is linked to this class 0 for evidence.
At test time, we only evaluate on C bar.
Oh, at test time, you're actually seeing the same kind of quadrants,
Yeah.
but with different correlations. So you're going to see 0 with this car during training, but at test, you're going to see zeros and, let's say, trains for class 1, for example, and so on. And then they are labeled in different ways according to MNIST labels and so on. So, yeah, thanks for the clarification. So let's take 5-minute break from now. Okay, let's get started for the next half of the course, half of the lecture. So let's talk about adversarial generalization now. So now there is an adversary who's trying to make sure I do not recognize the object for some reason. Okay, and I wish to be able to still generalize well to these kind of samples. So first, a bit of motivation. Why do we care about having an adversary? So I'd like to start with this kind of observation. OOD generalization is kind of dealing with uncertainty. Okay. It's easy to kind of try to make a model generalize well in a single environment. But then the next question is, can you do this generalization for 2 different environments? And the number can kind of grow. 3 environments, any environments, or an infinite number of environments, or any environments, right? And yeah, how do we take care of this infinite number of possibilities? So we can conceptually think of the sizes of the space of possible environments that we care about. And that is also related to your knowledge of what's going to happen at deployment time. So if you have very little knowledge about what's going to happen at deployment time, then the space of possible environments is huge. It's also kind of similar to entropy concept. If you have more information, then you have less entropy. This is the hardest case. But as you have more and more knowledge about what you will have to take care later, then your space of possibilities will shrink. And that's kind of easier to address. So how do we deal with such uncertainty in general? When we do not know the enemy or the deployment environment, in this case, we have 2 choices. One is to make a guess, or the second method is preparing for the worst. There's no right answer here. It's just a matter of choice. So the pros for making a guess is when you make a very good guess, then you have a practical solution. You have a nice solution. But the con is that there's no guarantee that if you do not know if you're making the right guess here, then in the worst case, you're probably not making a lot of progress. What about preparing for the worst? The pro for that is that you're going to get some theoretical guarantees. You are kind of safe against the worst case scenario, and therefore for average case scenario, you're kind of good to go. The con against that is that it could be unrealistically pessimistic as well. So adversarial generalization is kind of machine learning technique for preparing for the worst when you do not know the target scenario, target distribution. So this is the formulation of general adversarial environment. We introduce the devil, which is choosing the hardest case for you. And I talked about this strategy space, right? Which is the space of possible environments. And what the devil will try to do is to find the worst environment for you. And there are three elements to it. So the goal, what is the devil trying to achieve here? And the second is the strategy space. What is the space where devil can make the choice? And third is the knowledge. What does the devil know about you? Because obviously, if the devil knows a lot about you, then the devil will make even more kind of worse choice for you than the devil doesn't know much about you, right? So when we talk about adversarial environments, we need to always talk about these three. Otherwise, we are kind of missing the critical ingredient. So yeah, this is the general formulation. Devil is picking something for you, some worst environment, and then you have your model here, which is trying to understand, trying to still recognize objects, for example, if your model is a discriminative model, and so on. And again, the advantage of having this kind of adversarial environment is that you have lower bound guarantee. So within this space of possible environments, because the devil is picking you the worst case scenario, if you have nailed this worst case scenario, then you know that you'll be better off in the other cases. But still, there is a big caveat, which is that your guarantee is still confined to this space of possible environments that you have been working with. So outside of this space, then you don't have that guarantee anymore. Was there any comment or? Okay. So let's jump into the first adversarial attack that we consider in the course. It's very simple, FGSM or attack, FGSM attack. It's fast gradient sign method. Fast gradient sign method. It's called L infinity adversarial attack. So let's see what the goal, space, and knowledge are for this devil. So the goal is obviously to reduce classification accuracy while being imperceptible to humans. And the space it considers is for every sample, you're going to make a very small perturbation dx with the norm L infinity of this dx smaller than epsilon. And knowledge is your access to model architecture and weights. Meaning that this is white box attack. This is called white box attack. So now we have this requirement that the attack should not be perceptible to humans. And that is partially satisfied by saying your L infinity norm of your attack should be, perturbation should be less than epsilon. Because, for example, this attack here is very visible for now, but if you take a scalar multiplication of 0.007, then it becomes very imperceptible to humans. And even if you add this image to the original image, you don't see much difference. It still looks like a natural image. And yet, if you apply this kind of change, your initial panda prediction will become a gibbon prediction with high confidence. So yeah, this is very iconic image from this Goodfellow paper. And this is called FGSM attack, because what you're doing here is, first of all, you take the input gradient of your loss function, right? Which is kind of encoding the direction from your input image, where the loss increases the greatest in the vicinity of your input. And then to make things simple, they take the sign for every pixel. So if that pixel gradient value is positive, then you take +1. If it's negative, then you take -1. And then you multiply this trinary or binary, so 3 values, right? +1, 0, and minus. you're going to have a map that consists of plus, -1, and 0. And then you take epsilon scalar for every element here. And then add this signed gradient to the original image. That's very simple, FGSM attack. It's also very cheap because you only need one forward pass and backward pass, and that's it. You generate the attack right away. And now let's talk about projected gradient descent attack, PGD attack. This is so far the strongest attack to date, I think. Also because not a lot of people continue looking into strong attacks anymore. But yeah, this came out in iClear 2018, and still this is considered the state-of-the-art attack. And this is LP adversarial attack, where LP is the norm, the name of the norm, where P is between 1 to infinity. And again, the goal is to reduce classification accuracy while being imperceptible to humans. And the space where it operates is now defined by this LP ball. So your perturbation size measured in terms of LP norm is smaller than epsilon. And here you need access to the model architecture and weights. So it's white box attack. So why do you need this kind of knowledge? It's because you need to compute the gradient, input gradient. And for computing the input gradient, you need basically the backwards function from this model. And for computing that, you need all structural details of your model and the weights. And so the devil knows kind of everything about you and then generates the most critical kind of direction based on your current status, theta values. And the optimization problem looks like this. So you're trying to maximize rather than minimize your loss function, where the object that is being optimized is that should be delta rather than x. Delta here, and such that there are some constraints. So the image should, after perturbation, should still look like an image. So the image should be within this boundary of 0 and 1 values for your pixels. And the size of the perturbation should be kept smaller than epsilon in LP norm. So devil is kind of finding your kind of solution, the worst case sample for every x in this epsilon ball within the LP, defined by the LP norm. And the way the algorithm looks like this. So, this is again signed input gradient as an FGSM. So you take the input gradient for the loss function first of all, and then take the sign and then some step size alpha here. So far it's FGSM, but then you do it multiple times basically for multiple t's. So you first apply to the original image and then do projection onto the LP sphere. Why do we do that? Because if you do this multiple times, then your solution can go beyond the LP ball. And whenever it goes beyond the LP ball, you want to project that back to the LP ball. So in a sense, you're kind of overshooting beyond this LP ball and then projecting. And if you take gradient ascent again, and then it overshoots again, and then you wish to project it back again, and then you do it multiple times. So typically you're kind of following the boundary of your LP ball when you do this. And then if you do this multiple times, then obviously you're going to find a much better estimate of even more worst case sample for your model compared to, let's say, FGSM, which is just single step method. Yes.
Wouldn't we simply just use the sign of the gradient? Why don't we also use the gradient?
Yeah, I think either case works. I tried both some time ago, and both of them are quite strong. But Yeah, I think for some reason they decided to just take sine here as well. Yeah. But actually, it doesn't matter too much either because, you know, Adam optimizer instead of SGD, Adam is also taking the sign of the gradient for making updates. And that still works very well. It's also one of the state-of-the-art optimizers. So I think for this kind of convex optimization problems for high-dimensional variables, taking sign or not doesn't really matter too much. And it's usually a choice that you make based on your empirical observations, which one is working better for your purpose. Yeah. Yeah.
How would you choose the size of the region which you want to project here?
Typically very small value, and you wish to probably fix this size across different studies, because typically you wish to kind of compare against the previous attack or defense, and there are some values that are kind of unified in the community, and typically you just follow them. It doesn't matter too much because anyways, it's not visible to humans if they're kind of small enough, right? So now comparing FGSM and PGD, if you look at this optimization problem, it's also a non-convex problem because the loss function is non-convex not only with respect to the theta, the model parameters, but also with respect to the input x. Right, so this is a hard optimization problem. So there's no guarantee that your gradient descent or ascent algorithm will find the optimal solution. Even within the epsilon ball, even if it's really tiny ball, right? But it's a high dimensional space. So effectively the space is exponentially large still. And so it's a very hard problem. And therefore, the strength of the attack depends a lot on the optimization algorithm. So it's not like whatever gradient descent method you're going to choose, you're going to find the optimal. It's not the case. And you have a lot of design choice for doing this optimization. And this PGD method is generally much stronger than FGSM. And that means PGD finds much better optima than just this one-step gradient. Yeah, and PGD is still the state-of-the-art now. Okay, so far we have been talking about strategy spaces defined by LP ball. But LP ball in which space, right? It's in the pixel space. And if you take the LP ball in the pixel space, it's not exactly aligned with human perception. It's missing some of the changes that are not visible to humans. And it's capturing also way too much in some cases. So I can give you some counterexample for LP ball as a human perception. So the question is, which pairs look more similar to each other, right? These two or these two? And yeah, if you measure in terms of L2 distance, which is just taking the difference between the pixel values in the corresponding coordinates and taking the norm, L2 norm, the right figure has much higher L2 distance. Well, these are actually not the real values, but I just, obviously, yeah, I just made some values. But this is the real problem, and these guys at CPR 18, they also came up with this perceptual metric that's beyond the LP ball or any other measure.
So,
sure.
So we call it a problem because we want to like be adversarial with regards to human perception.
Yeah. So the goal for the adversary is to produce something that is imperceptible to humans. If that is the starting point, then
we minimize perceptibility. Like we want to minimize the likelihood that somebody recognizes that we've messed with the image.
Yeah. So let me give you a scenario. So let's say your model is perfectly defended against any kind of LP attacks, right? But then still your adversary can find one pixel shift of your image, which is going to be imperceptible, but not defended yet by the model, because the model is just focusing so much on this LP small attacks, right? So it's kind of based on this kind of scenario where you're kind of targeting human imperceptibility. We are finding kind of counterexamples where the adversary can kind of take advantage of, like exploit this kind of blind spots of your model. Yeah, so generally like 1 pixel shift is very hard to detect for human eyes, right? But that generally results in huge L2 distances because your images are not like smooth overall, but it's usually there are clear boundaries, and along this boundary you're going to introduce a lot of L2 distance changes by shifting 1 pixel, right? So the question is, can you actually define a metric that assigns very small distance to image translations, for example? Of course, there are also other image transformations that's introducing very small changes for human perception, but still introduces a large LP distance. But for now, let's probably talk just about these translations. And one way to measure this translation very well is optical flow measure. So what is optical flow, first of all? So optical flow measures it's used a lot in visual tracking or in videos in general. So for 2 consecutive frames, you wish to do the matching of pixels across frames. So which pixel in the image is kind of has moved to another location to make the scene into the second frame. So let's say there's kind of a cloth that's kind of or easier cases, if there's a rigid object that is a ball that is kind of flying across the sky, and for 2 consecutive frames, the ball pixels will not change much per se, but it will translate by a few pixels in the next frame. So the task here is to find the exact pixels in the first frame and the second frame that are encoding the same kind of patch in the image, same position in the ball. And by using optical flow estimation, you can also kind of find these correspondences. And then after finding the correspondence, what you can do is to measure the pixel-wise distances. So for each pixel that is kind of transported, you measure the distance. And then you take the average of the distance that every pixel in your scene is making. And then that's going to give you an idea of how much warping has taken place from scene 1 to scene 2. Okay, so typically you kind of measure that for video frames. So for this kind of figure, frame 1 and frame 2, you're going to measure optical flows, and they're encoded in terms of colors. So color here is the direction, and the intensity is the magnitude of the vector. So in a sense, you are measuring a vector field as a result of measuring optical flows. So how can we use this framework for finding adversarial patterns? So instead of estimating optical flow from 2 consecutive frames, we can also solve the problem of making the next frame based on the previous frame and the optical flow, right? So given the first frame, according to your estimation of optical flow, you can generate the second image by moving pixels in respective directions. So eventually what you do is for every target image pixel, you find the corresponding flow vector for that pixel, and then you kind of trace back which pixels from the original image the current pixel should be made, right? And then after crawling all the pixels that should be kind of making the current pixel, you take bilinear interpolation. Okay, so that's how you make your second frame here. And here you optimize for the flow here. And the flow is optimized in such a way that your perturbed image according to these pixel flows should be not recognized by your model. Okay, so instead of finding your additive perturbation, that's going to fool your model, you're finding a pixel-wise movement such that when you apply that movement to the current pixels, the resulting image will fool your model. Okay. And somehow you wish your movements of your pixels to be very small. And this can be regularized by using total variation, for example. It's kind of a generalization of L1 norm for vector fields. Okay. Well, it's actually L1 norm for the gradients, the directional gradients of your vector field. So if your vector field is kind of all aligned to the west, to the west, then there's no total variation at all because the gradient is 0 because it's a constant map. But if there's a sudden change in your gradients in your map, then your total variation values are higher. Okay, so the intuition is that translating everything to a few pixels should not be considered a huge norm, meaning that it's not something that is so human perceptible. So at least for the translation of image, this total variation measure over the pixel-wise translation is a good proxy for human perception. In other words, yes.
At the borders here, you will simply copy a pixel. Right?
Yeah, those kernel cases, yeah, you have to copy pixels from the boundary pixels. Yeah. Okay. So we looked into this LP space or this warping way of making attacks. And there can be so many different ways of formulating your strategy space to attack your model. But we have to think about the real world scenario for these kind of attacks. Is it plausible at all? Right? Because if you think about it, what we're doing is we are perturbing pixels for a digital image after this digital image is captured from the real world. You're downloading your dataset samples from, let's say, Flickr, for example. If you're using ImageNet, ImageNet is from Flickr. Also, Coco is from Flickr. Yeah, they're all from like some digital search engines for images, right? And we are studying the impact of attacks on those kind of digital images. What kind of real world scenario does that correspond to, right? So if you think about the full pipeline of an object in the real world being recognized by a model, actually there is a sensor that's taking the image in the first place, and then the digital image gets processed by the model. And your kind of your adversary is somehow like kicking into this stage where the digital image is fed to the model. Does that make sense at all, right? And does it make sense to try to defend against such an adversary? Because, for example, we can just make sure that there should be no perturbation that's applied to your input image at all, right? And for doing that, you just need to make sure that no one really comes into my compiled code and makes changes in the data stream and so on. And that's just basic information security, rather than making your model safer by adversarially training it or doing something weird, right? So yeah, the other case is when the user has an image in their local computer and then tries to upload it on cloud. And then this image on cloud is recognized by the model. Still, it's kind of hard for any kind of adversary to come into this pipeline and make changes. So what I'm saying is by focusing on LP kind of attacks, we are probably looking at a problem that is not existent at all. Okay. So now people agree with this kind of viewpoint as well, and they also look into other types of strategy spaces, like physical spaces. So they try to put these kind of stickers on the stop sign, or some painting, graffiti on stop sign, to make sure this is not detected by automatic self-driving cars. And also, some people also made this kind of pattern that you can carry around. It's poster. And then the person who's carrying this sign does not get detected by this YOLO detector. Okay. That's probably more realistic, right? If adversary is kind of intervening into this object in the real world, then that's probably more plausible attack, and we should be focusing on defending against these kind of adversaries. Right. And then there were also other strategy spaces people looked into, such as object poses in the 3D world. So an adversary comes in and tries to kind of change the pose of some objects, right? Just to make sure it's not recognized by some automatic systems. And that could be a real threat, right? Yeah, and in this case, you do not necessarily care about small changes in the object space, because object pose, because because what's the goal of human imperceptibility, right? The original reason why we were caring about imperceptibility was because if it's too obvious to humans, then they can already come in and do something, right? About these kind of images that are changed. Yeah, but actually, I admit I cannot think of any plausible scenario for these kind of objects in the real world, but yeah. But now here, what is very interesting is that we are kind of in the boundary between adversarial robustness and cross-bias generalization, or the kind of generalization problem that we are looking into, right? So if the perturbation goes larger, and if we do not anymore have some notion of worst case enemies and so on, then we are also in the realm of kind of generalization in general, against biases, and so on. Okay. So yeah, the remark here is people are looking into different strategy spaces as well. Now let's discuss a bit on the knowledge on the target model. We have been looking into white box attacks, meaning that the adversary knows all the model details and the weights, and therefore can compute input gradients. And if you can compute input gradients, you can do all kinds of strong attacks like PGD. Right. So the adversary this is also kind of not so realistic, because when you have a machine learning model as a service somewhere on the cloud or as an API somewhere, then they would never let you look into the details of the model, right? Because first of all, they are intellectual properties, so you should not be looking at them and copying them. And also it exposes the model to all kinds of attacks like these ones, right? And a quick solution to that is not to open source it or not to release it, not to show it to anyone, right? So for that reason, people are also looking into black box attacks rather than white box. The condition for black box model is that you can only observe the inputs and outputs to a model. And this is actually fairly realistic because many real world applications are based on API access. You give an input to the model and then you take the output from the model. Of course, there are some realistic limitations for the adversary, which is the number of queries that you can send to this model it's called rate limit. And also, yeah, if you, like, let's say it's a face model, like recognizing you in your personal photo albums. And let's say you're sending all kinds of weird patterns like random noise and so on, right? These are super detectable by the system, and if you're caught in like sending non-faces too much, then you can be blocked out of this service because obviously you're very suspicious. So yeah, these are limitations to keep in mind. And of course, with less knowledge about the model, the attacks are much weaker than white box. A few examples these days, GPT-3. So you can give an input to this GPT-3 and then produce output later on. If there's a way to kind of attack this kind of GPT-3 based on input and output pair observations, then that's going to be very interesting. DALL-E as well. Yeah, you give an input and then you get the output back. So how can you attack this kind of model, for example? There are several stages that you should follow in this case. So the first stage is you first prepare a set of inputs that you wish to give to the model, right? And then you give them to the model and observe the corresponding outputs. And then you're going to have a lot of input-output pairs in your local computer. And based on the input and output pairs, you train a new model, ideally trying to follow the same architecture as the target model. So for example, if you know that the target model is kind of using transformer, then you probably wish to also use transformer model. And then based on these query input and output pairs, you train your substitute model, G. And the assumption here is that your substitute model G will be very close to the target model F, which is unknown, okay? And after doing that, what you can do is you prepare some query input to turn it into an attack. And then using this substitute model, you generate an output that's attacking your substitute model. And you trust that this attack will also attack your target model F because of some transferability of your attacks. Okay, and then you are successfully attacking this black box model out there. Yes.
You know, if somebody actually tried it with like really large scale models, like the GP or the DALL-E or something.
So you're asking if I have tried or someone else?
It's like really large scale model, like the paper about like doing like I can really see this like smaller models, simpler applications upon like really large thing, like like a big effort.
Yeah. I think so too. To be able to attack those kind of large systems, you probably also need a very large substitute model, for example. And you can even just count the number of companies that can do this, right? And if someone does that, then probably it's very obvious who did that.
You recognize them
You recognize, yeah. But I think they're focusing more on other types of problems nowadays than this kind of black box attack, because they already have tons of other problems to take care of anyway. So, for example, like private information from training data pops up in your generated outputs, and these bias issues and explainability and so on. So, and yeah, I think they are probably more realistic than, for example, the worst case scenario that can happen with this kind of attack, for example, is the performance drops. But I don't think the adversary's goal is in any realistic scenario to reduce the performance for me, right? So I think when it comes to, I mean, it was 2017 when this paper came out, right? And during that time, this kind of attack was more focusing on theoretical possibilities, right? But nowadays we are focusing more on the realistic threats that you have to deal with these kind of large models. And so I think the shift has focus has shifted. Yeah. Right? So yeah. So that's one way to attack this black box model. The other attack is called zeroth order attack. You still wish to generate some kind of gradient, right? And actually, with a lot of API calls, you can generate gradients if you do numerical approximation of the gradient. So there are, let's say for 200 by 200 image, you have 120,000 pixels, including RGB values. So if you do 120 times 2 API calls, then you're gonna reconstruct the numerical approximation of your gradient fully for this input. So theoretically, it's possible, but in practice, that's very costly, and no API will let you call it more than 1,000 times a day, I would say. So yeah, it takes forever to compute this. But you can also be smart and try to pick pixels that are generally, for example, you can train your local model that's predicting the pixel that is most likely to generate the highest kind of response from your model. So for example, by preparing a lot of models in your local machine, and by training a model that is trained by the pair of images and the corresponding pixel that's attacking as many models as possible in your local machine, right? If you have that kind of pair data, then you can train a model which knows about general information about which pixels are likely to be very vulnerable to general machine learning model. If you have that kind of knowledge, then we can probably use that to choose the pixels. And for every pixel, we can compute how to, we can do API calls, right? And then find the values of perturbations for that pixel that's giving me the right response from the API. So yeah, that's exactly this algorithm. So the second line says randomly pick a coordinate, but this is usually not very efficient. So if there is a smart way to kind of pick the coordinate here, then you can kind of dig into that coordinate by doing a few API calls to this black box and finding out what is the right perturbation for that pixel. Okay. Yeah, that is one interesting direction for black box attacks. Now, defense. How do we defend against such adversaries? People talk about adversarial training a lot. So adversarial training so far is generally perceived as the best working defense against LP attacks. So what you do is you minimize this loss function here. where you're actually you have a minimax formulation. So you're minimizing for your loss theta, but at the same time, you're maximizing your loss for loss with respect to this perturbation delta for every x. Okay, so in practice, what you do is you do a few PGD steps for every sample, and then generate an attack, and then use that attack for training your parameters. Okay. So when you do that, so this is a kind of nice summary of the effect of adversarial training. So I'm going to try to see a few conclusions from here. So the first thing to observe here is the impact of adversarial attack. So we have three cases here. Natural means there's no attack. And then FGSM attack, which is very weak. And then there's PGD attack. Okay. So in general, and what is shown is the MNIST accuracy here. And A, B, C, D, these are after different training. So A is just normal training. B is after FGSM adversarial training, meaning that you have trained your model with FGSM attacked samples. PGD training means you train with PGD samples. So for this vanilla training model, any kind of attack pushes your score down close to 0. Although FGSM is slightly weaker than PGD. PGD just gives 0 for every sample, right? So the impact of adversarial attack is very strong, right? Yeah, pushes down all the scores to close to 0 from close to 100. Now, impact of adversarial training. So we can look into this axis from A, B, C to, right, A, B, C. And if you train with FGSM samples, then we see that still FGSM, well, actually FGSM samples are close to 100 now, right? After training with that particular set of samples. Yes?
Is this training only on adversarial samples?
So there are different versions. I'm not sure if they choose this version, but
This one feels like the natural one drops so much.
yeah, usually there's a trade-off, even if you mix the samples. Yeah, if you do adversarial training, you should expect a few percentage point drops in your natural accuracy, actually. Yeah. You cannot be good at both of them. And actually, there's a lot of studies on this trade-off as well. Yeah. Yeah, that's a good point. And actually, even if you train with FGSM samples, PGD attack breaks the system fairly well still, right? So in a sense, PGD is a much stronger attack than FGSM. We can confirm that here as well. But if you train with PGD samples, then we have fairly nice adversarial accuracy, even after attacking with the strong PGD attacks, right? So it's good. It's kind of working. Now let's take a look at the impact of model capacity, meaning how many parameters you have in your model, right? So there is a scale from 1 to 16. And we can see that the PGD attack is breaking down the system still when the capacity is small, even after adversarial training. But if the scale is large, then the adversarial training is even more effective. I think this is general kind of lesson that people learn from a lot of different versions of adversarial training results. That for adversarial training, you really need a high capacity model, right? That also kind of means that you need much more, like you need to be able to take care of much more complexity in your kind of data distribution when you need to train with strong attacks. Because, yeah, there are probably much more complexity in your decision boundary. And finally, we see interesting trend here that for depending against a particular attack, you need to train with that particular attack in general, right? Because you see, for naive model, natural model, the natural samples are the best, but if you train it FGSM, then the vanilla samples have much lower accuracy now, right? So in a sense, you need to have the right match between the target distribution and the training distribution. Yes.
So you just said that the decision boundary becomes more complex because of this adversarial training. This makes perfect sense. But then I thought, does it also make sense that this means that training for one attack makes the model more brittle to all the other attacks because of this complexity that is added?
Yeah, maybe. I'm not too sure. Yeah.
Like this connection with different types of
Yeah, I don't remember any paper discussing the impact of different attacks on decision boundary complexity or the complexity of loss surface, these kind of topics. But I can imagine you should be able to find some paper on that as well. Yeah. So, and generally adversarial training is perceived as a very expensive defense mechanism because let's think about per batch complexity, for example. How many forward and backward steps per batch do you need to make, right? Compared to just training vanilla way. For training vanilla way, you just need one forward pass of the batch and then backward pass, and then you update the parameters. That's it. But if you wish to adversarially train it, you have to do forward and backward passes for every step for finding the PhD sample. So depending on how many steps of PhD you do, you're adding T steps times the original number of forward and backward added here, right? And for training, yeah, you're doing right, per batch is of course T times more expensive, and therefore the whole training is also T times more expensive. But at the same time, you might need more epochs to train the model because you're solving a harder problem. And so apparent complexity is times T, but also there's added complexity of having to add more epochs for your training. But at inference, everything is the same. So just one forward pass. So as long as you train something in an adversarial way, then you can just open source this model and let people use it. Yeah, that is possible. So I guess for the interest of time, I think we stop here and then resume from obfuscated gradients from next time. Okay. All right, then. Thanks, guys. And yeah, see you next week then.